seat. Let's get started. Okay. So the next lecture is a little bit more theoretical. It's a skill-based analysis of emergence of complex skills in LLMs. So just as a reminder, we talked about the bigger lesson by Richard Sutton. In 3 words, it says bigger is better, but it's more subtle than that. Bigger is necessary, but not sufficient, because the training method should be able to exploit the skill. And as we discussed in the first lecture, next word prediction just happens to scale. Like you keep, when you increase the scale, it keeps improving. Although one hears that industry people finally scale it enough that improvements have plateaued, but that has not been released. But that's what one hears. Okay, so now emergence. This was mentioned in the previous 2 talks as well, that as models were scaled up, it was seen that they display suddenly interesting behavior, and those behaviors arise at that scale. That's flops on log scale, on the x-axis. And this, in this case, it was these in-context learning examples where you can suddenly do modular arithmetic or word and scramble, etc. Okay, so it emerges roughly in tandem. So suddenly, at some scale, they got interesting behaviors, but not all. Other behaviors emerge not later, like question, answer, emotion behavior. All right, so we talked about scaling laws, and I drew them as a cartoon in the first lecture, but there was a precise mathematical expression. So there were several papers, starting with Kaplan et al., and then this paper from DeepMind, Google DeepMind, Hoffman et al., the chinchilla scaling law, gave a very nice expression. And actually there was a mistake, not mistake, but like the misestimation there, and the expression I'm giving it from is from a follow-up paper. And on the left you can think of it as error and next word prediction, which is a cross entropy. And on the right is this expression. N is, so I don't have it here. N is the number of parameters. D is the data set size in tokens. So you see it's roughly like a third, okay, the scaling, inversely with the cube root of the number of parameters and the cube root of the data set size.
That's experimental?
This is experimental, yes. As I was describing, you do experiments at some scale and extrapolate. Yeah, so there's no theory for this, where this arises from. Although, you know, in general, for all of machine learning, like there's some inverse polynomial dependence on the data set size in general. And the parameters. So this cross entropy, how to think about it? So there's a constant term. So the constant term corresponds to the inherent entropy of English or whatever language. That the next word prediction task inherently has some entropy. You ask a billion people and you generate from their answers a distribution, and there's an inherent entropy there. And then the rest of the part is the part that you can reduce by scaling. And this for GPT-3 was already pretty small, 0.05. Okay, so now you stare at it and you realize when you increase the number of parameters of the dataset size, you're only changing this 0.05, which is only less than 4% or 3% of the total, further and further. You're squeezing it out more and more. Okay? But this is an important part, because the inherent entropy you cannot reduce, and this is all you can grow. And this, information theoretically, I won't do the derivation, is the KL divergence between the human distribution for the next word and the model's distribution. Okay, there's an information periodic quantity, K of divergence, and you can think of it as excess entropy. Okay, so the key fact here is if you do the math, if you do 10x scaling, you know, because it's n to the 0.3 or something, 10x scaling roughly halves the excess entropy. Okay? So this is saying that as you keep scaling up, you will keep halving the entropy with every 10x scaling. And this law works for several orders of magnitude. Okay, so those are the two pieces, that there's a scaling law, which gives some kind of continuous improvement with scaling. And then this phenomenon that somehow it's more discrete, that at a certain scale, interesting behaviors emerge. At another scale, other interesting behaviors emerge. Now, by the way, nobody thinks that that emergence is completely discrete. It's sort of it's a continuous thing, but when you're plotting it on log scale, it's more like a jump. So we want to understand this a little bit better, so that you can predict some interesting phenomena. And so that's what we did. This I forgot to say, maybe I had it already on some slide. This was work with Anirudh Goel at DeepMind. Yeah, I was on sabbatical at DeepMind in 2023. So here are the hurdles. So mathematical analysis of deep learning is in its infancy. Also, we are interested in new capabilities, tasks not seen in training. And that, generalization theory doesn't really apply, right? In machine learning, we have generalization, but this is like the new capabilities, whatever that means. And then when you start thinking about it as mathematically, okay, machine learning requires data distribution. So what's a data distribution? The language corpus, right? This hodgepodge of stuff collected. So it's some distribution, but mathematically, what is that? Nobody knows, right? How do you mathematically describe the language corpus? And then what are skills, right? New skills that are emerging. How do you formalize those? All of these are mathematically very, very big. And even for language semantics, people have all kinds of discussions and arguments about how to even formalize semantics. So they are all those things, but then anyway, they don't connect with network prediction. They never consider network prediction. So we have to come up, somehow develop theory in that context. Okay, so let's just think about skills, capabilities, and network prediction. So here are the following assumptions. Okay, and I'll repeat them also in the next slide, but I'll list them all here in the theory. So as I said, you can go and ask experts what is a skill, nobody will be able to give you a correct answer, an exact answer that they all agree on. So we just assume there is a ground truth set of skills S needed for text comprehension. And we're thinking of it as discrete. Probably the set of skills is continuous. That's why there's no discussion. There's so much disagreement. But okay, think of it as discrete. And for simplicity, we'll think of this training or text corpora, the text corpus, as being divided into pieces of text. Okay, so like maybe one context map. And that involves cases for some case. Okay, and for theory, you need simplifying assumptions, so it's K. It's the same for all these pieces. And we say that the model understands the text piece if it obtains low excess entropy. Okay. Now remember that excess entropy was this thing that was going down with scale. So as you scale up the model, the excess entropy goes down. Oops, sorry. Okay. That. Now, what is competence at a scale? So we're assuming that ground truth, there's some skills associated with every text piece. So if I take a skill, I don't know, metaphor, use a metaphor. Competence at that scale is low excess entropy in text pieces that involve using metaphor. Okay? It may involve all kinds of other skills, but all of these text pieces that involve metaphor, I look at the cross entropy there. Excess cross entropy. And now, they are complicated skills. So like use of metaphor is one skill. But what about a more complicated skill where you have to use metaphor and it should have some other linguistic property? That is a complex skill. So when you're asked to use multiple skills, and that's a complex skill. So it's a subset of K-prime skills. And competence at this K-prime complex skill is just the next word prediction. Sorry, I meant crossing. Okay, so it's a low crossing, low excess entropy. I'm sorry. Same as number 4. Low excess entropy on these text pieces that use those K-prime skills. Okay, so this, again, to summarize, text corpus is divided into pieces of text. Each piece of text has involves some underlying set of skills. Set of skills is S. And if I'm interested in competence on a certain skill or a subset of skills, I look at text pieces that involve those, and then look at the excess entropy there. That's the point of the measure. Yes?
What's the difference between the third and the fourth one?
Third. Yeah, so third is not a formal definition, understand. Yeah, I'm just quantifying for you that I'm equating understanding with low excess entropy. It's nothing more. Okay? All right, so illustration. This sentence, which is actually from the GPT-4, in the labyrinth pursuing, you can read it. Right. Suppose nature produces sex using the 3 tuple of skills. Okay, so K is 3. Then the overlapping tasks in this are the one skill task, right? Each of the individual skills. So this understanding this requires 3 skills. So it's in the one skill task. Okay, so there are 3 one skill tasks. 3 choose 2 skill tasks. 3 choose 3 skill tasks. Maybe the task itself. Okay, so this piece of text is actually in many tasks, corresponding to different skills and subsets of skills. Any questions? Yes.
So 3 over 3 is 1, right?
That's just 1, yeah.
It's 3. So could you again explain what you mean by task or by skill?
Okay, so I won't explain what a skill is, right? Skill is just some ground truth thing. Yeah. So this test, suppose this task contains 3 skills, right? Mm-hmm. Then there's a task corresponding to each of the individual skills, each pair of skills, and the triple of skills. That's all. There are many tasks, right? So remember, they were complex tasks, right? More and more skills. So this piece of text is involved in all of those tasks.
I still have some problems to quantify how you get like 3 skill tasks. That's one.
Okay, so let's say there's 3 skills A, B, C in this text.
Okay.
It's in the task for skill A, task for skill B, task for skill C. Yeah.
Okay.
And then A, B, B, C, C.
That's it. Okay, thank you.
I should have said it. Any other questions? Okay, so now I'll tell you in an intuitive way what the emergence law will do. Okay? So this is the paper with Anirudh. So complex skill I already said is some couple of skills, 2, 3, 4, or one skill. So the emergence law says the following. That's what we proved in our theory. That if models of a certain scale have a certain competence on K-prime tuples, so competence with respect to this excess entropy measure, have a certain competence, then a 10x larger model will have a similar competence on twice as many, tuples of size twice as much. So like if K prime is 2, so it has certain competence on pairs of skills, then the 10x larger model will have similar competence on 4 tuples of skills. So you double so in one line, you scale up the model by 10x, and you can double the number of skills on which the model shows competence. Okay, so when solving a task, you can apply 4 skills reliably. Yeah. point this out. So suppose there is some set of skills, 10,000, 100,000 skills, whatever. The number of k tuples of the set of skills grows as the kth power of the number of skills. Right? So if this scaling continues to hold, the set of these k tuples grows exponentially with k. And the data set is not increasing at that rate, right? It's increased by 10x, 100x, right? But this is in the exponent. And so models learn compositional skills without having seen all possible skill combinations. That's what this is implying. Now, this phenomenon, I mean, it's intuitive that once we know how to apply a skill, we can apply 3 of them, 4 of them, etc. We can do that also. I learned that very quickly. And this pertains to an old debate about human language, which Noam Chomsky, maybe the father of modern linguistics, argued many years ago that humans have this ability to compose linguistic skills. He was talking about grammar. And that we don't have enough training data, to learn the composition, because there's so many compositions. And so his argument was that this means that there's an innate grammar that's in our head. Okay, this was an old argument, and now people don't believe it so much. And Chomsky himself was forced to not retract, but pull back from that claim as much. But still, he kind of believes that. But the point is, the language models also have this kind of exponential learning. Okay. All right, so here's a test of the theory's prediction. The skill mix evaluation. Namely that as you scale up, you get competence on ability to apply many skills in the same task or in the same piece of text. And this was with Princeton students and 2 DeepMind colleagues, Jonah Brown and Henry. So the skill mix evaluation, I gave an example before, but now maybe you see it more clearly. So there are n skills. We start with n skills. And why did we choose them? They appear in articles in Wikipedia. Articles on linguistic skills. So these are named and described in Wikipedia. So every model, big and small, has extensively trained on Wikipedia. It knows them. Okay, so it was, I think, about around 100 or maybe 200 skills in that evaluation. Then we chose topics, and how did we choose topics? We estimated their frequency, and we chose topics which were sort of okay, but not very frequent. So sewing, gardening, etc. So again, something every model would know, but not extensive data on it. And now you randomly pick some set of skills and a topic, and ask the model to generate a short text about sewing that exhibits these 3 skills. Okay, and you can increase 3 to 4, 5, whatever. So that's the skill mix evaluation. And remember, our prediction is that as the models get larger by each order of magnitude, you'll see different behaviors. So Llama 270 chat had this. It didn't really quite do it. Llama 270B, at least it got the metaphor right. It was like trying to fit a square peg into a round hole. It's better. GPT-4. That's what you saw the sentence of. Much more intricate sentence, which uses these skills in a much more interesting way. This is all from 2023 summer. Okay, so models are much better now. The grading in this case for this evaluation was done by GPT-4, and we did some human spot check. So here were the results. So that's for pairs of skills, triples of skills, 4 tuples, 5 tuples, etc. So the Llama models, so even for pairs of skills, the small models struggle. The Mistral models were, not Mistral, sorry, the Chinese models at the time, like 20, were a little bit better. But like the better models could do pairs and triples of skills, but then they start struggling at k equals 4 and 5, except for GPT-4. So at the time, only GPT-4 was a very capable model. I mean, I'm not reporting fraud, etc., but they were also not very good. This is summer 2023. Okay, late summer. All right, so you see that GPT-4 is doing quite okay at k equals 5 and even k equals 6. So it's roughly like predicted by the theory. So Llama 270, X-Men 70 was 3 skills, etc. Now the interesting thing here is this was actually tough for humans. So we told ourselves, okay, we'll do a quick experiment amongst ourselves, how much we can do, how well can we do. And we gave ourselves 2 minutes to solve each question, right, for combining 4 skills. And we quickly realized we were testing each other. This is really hard. Like, to keep these 4 skills and the topic in your head and then construct there was a sentence limit too, so you could only use 2 or 3 sentences. To like fit all those skills into 2 or 3 sentences in that context of the topic was very hard. And then we said, okay, now we'll take like 8, 9 minutes, 10 minutes, just record whatever time we take per question. So it's actually very hard. Probably you get better, with practice, but without practice it was not easy. Any questions on this?
Okay, I have a question about the previous slides and also this one.
Yeah.
So, can we identify, for example, 2 skills as a new single skill? For example, I have skill A, skill B, and I say that skill C is the combination of skill A and skill B.
That was a couple. That's what I was saying. The complex skill.
So this means that can we say that we don't know exactly how many skills a language model has?
Correct.
Okay. So if we don't know how many skills a language model has, and we cannot enumerate them,
The set of skills, just to put my cards on the table, is continuous, I think.
okay.
I think it's a fallacy to think of them as discrete. Yeah, correct.
So why going large instead of try to explore and exploit all the set of possible skills of smaller models before going with larger models?
Well, that wasn't up to us, right? They already created the large models. So in terms of the study, we're just studying, how capability improves, right? I started with those plots that larger models have more capabilities, and we're trying to develop theory for it.
No, yes, but the question is, can I be surprised by the skills of a small model?
Oh yeah, I think so, yeah. And probably, this was 2023. Today, the 7B or 8B models are much better already, yeah. Okay, any other questions before? So, okay, the proof will be not really a very big proof. I'll just give you a very quick sketch. Okay, so remember this was the emergence law. Okay, that as you increase the scale, you have a certain then 10x larger ones than this. Okay, so this will improve using the chinchilla law, and the fact that 10x scaling will halve the excess. By the way, I forgot to mention, in the chinchilla law, they scaled up the data set size with the number of parameters. These days, so that was what was called compute optimal. But the proprietary models these days, they just train even the small models on all the data they have, basically. Because they don't need compute optimality, they want the best possible model. Because then that model is going to be used trillions of times for inference. So they want the best possible model for that size. So people don't use the chinchilla law to train small models. Yeah.
One short question is the chinchilla law an assumption or something?
It's an empirical law.
It's an empirical.
Yes. the way physics laws were in the 18th century, yes. Yeah. Okay, so yeah, so this is the plot. So I didn't explain this. So on the y-axis is mistake rate in applying the skill, basically the excess entropy, and quadruple of skills, has higher mistakes, pairs has lower mistakes, quantuples has even lower. And what the emergence law is saying is that when you do 10x scaling, the quadruple curve will shift down to where the pair curve is. So we have lower mistakes on quadruples of skills. And the pair curve will switch, it will move down to where the one tuple is. So its mistakes get lower. That's what the scaling law is saying. Okay, the emergence law. Any questions? Okay. So just to give you just a sense of the theory, we won't have any time for proofs anyway. So I already said that we are modeling the text corpus as a union of pieces, text pieces. Think of it as length, context length. And each of these pieces has some probability associated with it, mu t, but we don't know that. We don't know that even in practice. Because all you do is you just pick out pieces of text from the internet, you don't know what the underlying distribution is. That's unknowable. So, but it exists, okay, so nature knows. Then there's a set of basic skills, we don't know that either. And as I said, I don't even believe this set of skills is discrete, but let's continue with the fiction that there's some discretization. So there's some basic skills. And they could be whatever, linguistic, logic, science, math, whatever. So mu1s is a probability of skill s. This is also unknown. Okay? We don't know the distribution of skills. And it also depends on the corpus. We don't understand the corpus, we don't know the distribution. Any of these. But assume it exists. Here is the key assumption. How are text pieces generated? I'll say that in a second. First, let me just say this. We're thinking of a bipartite graph where each text piece has edges to the skills that are needed. Okay, this is some underlying graph, which again we don't know, but it's a mathematical object. Now, the statistical task associated with the single skill S is pick a random text piece adjacent to S and do next word prediction. Okay, so measure the excess entropy in that text piece. And the competence on skill S is the success rate on this statistical task. So now this is a simple task, it uses one basic skill. You can also use pairs of skills. So take a pair of skills, so for like those two pair of skills are adjacent to some pieces of text. You're going to pick text pieces adjacent to both S1 and S2 according to that distribution, that measure, and do next operation, etc. Any questions? Yes?
So the number of skills is discrete, right?
Is discrete, yeah. Sorry, is 3 you think? Oh, in each text piece. Here it's 3.
The number of skills is discrete, so it cannot be a continuous number of.
It's discrete, correct, yeah. Yeah, but maybe somebody here can sit down and work out a continuous version of this theorem. Probably is. Any other questions? Yeah.
What does it mean? Addition to both S1 and S2?
Oh, so scale pair is like one scale, second scale. So T is adjacent to both of them. So it involves using that pair of scales. So pair of scales is a more complex skill. In this theory, couples of scales are complex. Okay. Yeah, I realize that you only get an impressionistic view of the theory, but I'm hoping that will be still useful. Okay. So the wise person on the right is nature. Right? Nature knows all these things, the distribution, etc. We don't know anymore. Okay, what the set of skills is. We are just constructing a theory for nature. Okay? Nature knows all of that, but we don't. So our theory doesn't know what these measures are, or what the scales are. So okay, as I already said, it's measuring the excess entropy. So I already said that. Understanding of the text piece. And now this is a crucial assumption. What is the generation? So very simple, but key assumption for the generation. How does nature pick, these pieces of text? So it has some process where it picks a k couple of scales IID from this measure mu1 on property on the scales. So remember, there's a measure mu1 on the set of scales. Picks a k tuple by k rows, independent rows from that measure, and then uses some unknown process to convert it into a text piece T, and some unknown process to assign it a probability mu2. That probability. Okay. There's no pointer here, is it? No. That's not really. So that's it. Okay, so that's nature. We don't know nature, that's the wise person over there, but we're assuming this. So this IID, the fact that pieces of text are generated using independent rows from scales, is a key. Okay, everything else is completely unknown, only known to the wise person. But all we know is that it's picking k scales IID. And the way it's going to work is that this k means the scales being picked independently from this measure makes this graph a random graph. And there the statistics can be analyzed. Okay, that's random graph theory. That's where this is used. Now, the simple calculation of the model's average error is something like excess cross entropy. I won't do that. Let's go to the compositionality. Why does it emerge? So here's the key calculation. So there's a model of a certain scale. Oh, sorry, I took out the first question and I forgot. So ignore this first line. Just the excess cross entropy is high, some bigger than some. So there are these pieces of text, and the model is of a certain scale. And I've marked with X all the pieces of text where it has prediction errors. The model has some prediction errors, some level of prediction error. Ignore this close question thing. Sorry. And now I put an X there, okay? Just to think about it. Those are the places where the errors are. So as you scale up the model, you'll see fewer and fewer errors, right? It's making fewer prediction mistakes. So when you scale up by 10x, you reduce the number of errors by 2x, which means some of these x's go over. Okay? That's what scaling is. Okay? So there was some amount of errors, scale up, some of them go over. Right? So now intuitively, for most scales, or many scales, you'll see that there will be fewer errors in the text pieces that are in. But using random graph theory, you can get a very nice expression for it. Okay? That's the idea. That's where we need this key assumption, that these pieces involve random combinations of scales. And the calculation is via random graph theory. So this is a bipartite graph, and the randomness corresponds to the red nodes, which are text pieces, involve random subsets of k scales. Okay, so that's the random bipartite graph. And Y is a set of text pieces with errors where the model has high excess entropy. And so competence of the scale on a scale is a fraction of the edges that do not go into Y. And you can analyze that fraction using random graph theory, where this H is the entropy function, and this is called the competence curve. Okay, I don't expect you to take in this and make sense of it in real time. Just to give you an idea of what the expression is. How many people had ever seen random graph theory before this? Okay, not too many. So yeah, so it's a field in discrete mathematics where the graphs have randomly generated edges, random links. It's used, for instance, to analyze social networks as well. That's another famous application. And so it's used here.
consider instead of just like ANTA-post more complicated data structures, for example, tree? Because like it
Trees.
makes sense.
Hierarchies.
Hierarchies, yeah.
Yeah, so we left that as future work. It gets very messy. So as you can imagine, like math theory with just minimal assumptions and then see what you get out of it often give more clear insights than once you start. And then people say, okay, now why this assumption, that, so the chain of assumptions can get hard to reason about. Yeah. Okay, good. Yeah, this was just an example. How much money? Yeah, I should. Okay. Yeah, so that was decalculation. So when you do that calculation, so when you look at this expression, you plot it out. That's what that was plotted. So, this is like what fraction of scales and what fraction of edges, meaning that's error rate, and that's what this is plotted. And now this point I mentioned earlier, that the number of scales to the power k it could be more than the training corpus size. And indeed, in that skill mix evaluation that I mentioned, where we randomly pick skills and ask them to construct pieces of text involving those skills, there the number of skills to the power k was indeed more than the size of the training corpus. The training corpus is large, like 10 trillion or whatever at the time, but this was large. Okay. Number of skills to the power 6 is a very large number. And this was the power-D stimulus argument from Chomsky, where he argued that this power-D stimulus means that humans need to have this language organ, which we are born with. That was his argument, which now people don't. Yeah.
I'm trying to get a sense of this because
exactly.
I wonder if skill is actually a task. And now what we have is next word prediction task plus metaphor task plus chain of thought task. And so what we do with the training stages is combined with the task at the same moment. Is this multitask learning?
It's more complicated tasks. So when you have multiple skills, right? So like what you said, chain of thought, right? Chain of thought is a meta skill, but like chain of thought for math has some set of skills. Chain of thought for writing an essay has another set of skills, etc. So there's a set of skills. You are given, we're assuming that the corpus involves random combinations. Did I answer your question?
I'm wondering if we can train on a specific skill.
So your question is, can you train on specific skills? Good. I didn't plan that question. So what we showed was that just from sheer pre-training, models developed this ability to do mind skills. But actually the skill mix experiment was with instruct models, with chatbots, which have more than pre-training actually. So that was actually not quite exactly proving it. But anyway, so we became very interested in whether small LLMs can learn compose skills. And I must admit that at the time we came up with the theory, we thought that maybe it's hard to learn compose skills. Right? This is the Chomsky kind of thing. Like, there's too many combinations, it's very hard to learn. And it seemed hard to us to learn it as well. So actually, yeah, in the summer of 2023, we were unsure what the answer to this is. Like, can they efficiently learn to compose skills? How many people think that, well, okay, it's clear from the way I said it that what the answer is, okay? So we did that. So the setup was 101 leading language skills from Wikipedia under these categories. We took them. And these were the two models, Llama 13D and Mistral. And the paper is from 2024, but I think the experiments were from late 2023. So these were the good models back then. And the training data was generated by GPT-4 in response to requests to combine K-skills from categories, these two categories, literary and rhetorical. These are the biggest categories, 50 skills. Now you can see there are other categories which we haven't used in this training data. Okay, just these two categories, literary and rhetorical. But there are these other skills. Now, so we do that training, okay? So we train the model, next word predictor, right? The instruction tuning, and we train on that data up to triples of skills. And now we evaluate capability at generating text combining K-prime skills for different K-prime on the held out category. Why did we do held out? Because, I mean, we could have just done on training, but that would be so surprising. Here we wanted to understand whether it generalizes, this ability to combine skills, generalizes to new skills. Now, admittedly, they're still language skills. They're not completely new, but like, still, we didn't include them in training. So here were the results of fine-tuning on held out skills. So single skill data has almost no improvement. Okay, doesn't do any improvement. So, and I think that's because, you know, the pre-training data has lots of such data and we've already done. Pairs of skills is more rare, like within like 1 or 2 sentences. And so on pairs of skills, it improves performance on K equals 2 and 3. So remember, these are held out skills, and it's only trained on pairs, and it's being tested even on triples, and it's still generalized. And for K equals 1, 2, 3 triples, it improves performance on 3 and 2. So that's the performance numbers. So you can see here that from training on triples, performance improved on 4 and 5 as well for Mistral. Yeah, for Llama, it improved on K equals 4, but not so much on K equals 5. So that was kind of interesting. And we, as I said, we were not sure which way it would go. Any questions? Yes?
Yes. If I think of the whole problem as a probabilistic space,
Yeah.
when I have each skill separately, I can have the whole probabilistic space. But when I have now 2 skills that I want to look at, then I'm in a subspace of this probabilistic space that fulfills these 2 skills at the same time.
Yes.
So does this mean that the more skills I add, I hope that my model has this probabilistic space trained somehow, because it becomes more and more difficult to find this subdomain?
No, that's not true. Not clear. I mean, a priori it's not clear.
Yeah, but just then as the next question, if you have a smaller model, of course, which you then train on a lot of skills in particular, then should it learn, right?
See, what do you mean by train on a lot of skills? On examples with 1 K equals 1, one skill is
tuples, so like a very complex skill or complex task, because there is not many combinations that would fulfill all these.
Remember, these are held out skills. We're testing on held out skills. So your intuition doesn't apply.
Okay.
Right? It was not clear to us, a priori, what would happen. Right? So the question was, you know, what's the surprise here? The surprise in there is that's held out skills. So it's really learned compositional capability. Yes?
But this is all about fine-tuning. So you want to train on some.
No, as I said, for K equals 1, like it knows all the skills. All the models know all these skills. They were in Wikipedia. They train extensively on Wikipedia, even the tiny models. The individual skills they knew. It's just combining skills they knew.
Do you test the performance?
Oh, this is the same, you know, GPT-4 judge. Yeah. Yeah, it didn't help so much there, but I think, yeah, today I was trying many more things than I would have in 2023. Yeah, later. Okay. All right, so that's it. So it's stronger than predicted, and it generalized to k+1 and k+2 and whatever. Okay, so connection to reasoning training, lately, this has become very popular, and there's evidence that performance improvements come from improved ability to combine skills that the model already had. And it would be nice to extend the skill emergence theory to explain reasoning training. And conclusions, we gave the statistical theory for emergence, so complex skills. And complex skills are just ability to combine or compose basic skills. And the only basic assumption was that text pieces of the corpus are created by random process with many, many unknowns, the measure and everything. But it picks skills IID from a distribution. And then we got this implication from scaling laws that it doubles the number of skills that the model can combine. And we verified it somewhat in the context of these language skills. And we saw that models can learn compose skills from examples, only generalization. So in the third lecture, I'll talk about metacognition, which is also about skills, but the model's own discovery of skills. Okay, so that will be top line. Thank you very much. Yes.
I'm trying to put, especially the last part of what you were talking about in perspective. Is your point with regards to generalization that the model has an improved capability of composing skills in general, or is it a
Language skills.
What?
Language skills.
Yeah. Can you also then elaborate a bit on how you pick which skills are being held out versus those which are being held in? Because the claim is with regard to generalization in terms of general compositional capability.
No, we don't. Only the skills I mentioned. I don't say generalization in math or something. Only these language skills are going to be big.
I know, but if I think about the set of skills even in language, then maybe some skills which you held out are still similar or not completely orthogonal to others, or is that something which you do assume?
Yeah, I think I gave the categories. That's fairly different. Like theory of mind is very different skills.
Okay.
Yeah. So this is, by the way, also seen in this reasoning training. Like these new reasoning models. You train it to do reasoning on these verifiable settings where the answer is very easily verifiable, auto-checkable, and the reasoning generalizes to all kinds of other settings. They improve across them. So yeah, now this phenomenon is well known in the reasoning setting. Yeah.
Can you quantize the individual skills, let's say from 0 to 1, any skill through communication?
Like, can you reliably say, is the skill being used?
Or if we say whether it's still being used or whether it is not being used, like a complete negation of that skill.
So that's what I was saying, that it's not binary ever. There were settings where GPT-4 said, yeah, this skill is correctly used. We looked at it and we say, not clear. And there were settings in the other way. So there is a gray line, definitely, no gray region. So that's the question. Yeah.
Perfect. Thank you very much.